Hello, this is Dr. Hanaa Assil, and today we're doing the June 2021 paper for Unit 3 in the IAS Edexcel Chemistry. So the first question was the white solids, sodium sulfate and potassium carbonate, may be distinguished using a flame test. Identify material from which the flame test wire could be made. Remember, when we're doing the flame test, the wire should be made of something like platinum because it is inert and it has a high melting point, so it will not melt in the flame. Describe how to carry out a flame test. How do we carry out a flame test? We said clean a platinum wire by dipping it in concentrated HCl, then dip the wire in the salt, and then expose the wire to the non-luminous flame of the Bunsen burner. Now he's telling me that the substances we're talking about have sodium and potassium. The sodium should give us a yellow flame, while the potassium gives a lilac flame. Then he says sodium sulfate and potassium carbonate may also be distinguished using chemical tests. So he wants chemical tests for the anions. That means he's asking for test for sulfate and test for carbonate. What was the test for sulfate? Add dilute nitric acid and barium nitrate solution, or we could also say dilute hydrochloric acid and barium chloride solution. If I have a sulfate, a white precipitate is formed. So a white precipitate indicates the presence of a sulfate ion. Now, what was the test for carbonate? The test was carbonate was add an acid. So specify an acid, dilute HCl, for example. You should get effervescence or bubbles of carbon dioxide gas that turn lime water milky. That would indicate the presence of carbonate ions. Then question 2 says this question is about the reactions of 3 compounds that have the formula C6H12O. The compounds are these 3, and he's saying give a chemical test to show the presence of OH group in all 3 compounds. Now you should remember the test for the alcohol. For the OH group, we should add phosphorus pentachloride or PCl5. If I have something that has an OH that includes an alcohol or an acid, we end up with steamy white fumes because hydrogen chloride gas is formed. Then he says give a chemical test to show the presence of carbon-carbon double bond. What was the test for carbon-carbon double bond? It was add bromine water. The color changes from reddish brown to colorless. Remember, this is the test for alkenes or the presence of C double bond C, or remember, it is also the test for unsaturation if he's saying test for unsaturation. The next question says the test you have given is repeated with 1-methyl cyclopentanol. Now let's remind ourselves which one was 1-methyl cyclopentanol. It was that compound. Now, if I do this with bromine water, again, we said the bromine water test is one for double bond. Does this one have a double bond? It doesn't, so there is no change or no reaction. And then he says separate samples of each of these compounds are warmed with acidified potassium dichromate. Now, remember, acidified potassium dichromate was what? It was an oxidizing agent. It oxidizes primary or secondary alcohol. Remember that a tertiary alcohol would not react with an oxidizing agent. So that first compound, it's a what? It's a secondary alcohol. It would react if I put potassium dichromate. It will change from orange to green, and that is because the secondary alcohol is oxidized to give a ketone. Remember what's a ketone? There is a double bond O instead of the bond going to the OH. Then this second one is what? It's a primary alcohol. Yes, it will be oxidized. So the dichromate will change from orange to green because the primary alcohol forms an acid. Now that last one is a what? It's a tertiary alcohol. Tertiary alcohols cannot be oxidized. So if I put potassium dichromate, there is no change. This next question is about infrared. He says spectroscopy provides information about the structure of these three compounds. He gives you the table that shows all the position of the peaks. Identify the wave number range and the bond responsible for one peak which you would expect to see in the IR spectra of all three compounds. What were the three compounds? These were the three compounds. They all contain an OH, so you would expect the peak for the OH in alcohols. And from the table, it says it's the peak from 3750 to 3200. This is because they all have an OH group. Then he says identify the wave number range and the bond responsible for one peak which you would expect in the IR spectra of only one of these compounds. Now, what is the difference between them? Only one of them is an alkene. Only one of them has a C double bond C. So only one of them will have a peak at 1669 to 1645. This is from the table for the C double bond C. Give a reason why there is a peak at M over Z 100 in the mass spectra of all three compounds. Well, what was the formula of all three compounds? The formula was C6H12O. And if you calculate the MR of that, that is 100. So you would expect an M over Z peak at 100 for all three of them because they all have the same molecular mass. Then he says fragmentation of 1-methyl cyclopentanol results in a significant peak at 85. So just the structures of the two species formed when one bond in 1-methyl cyclopentanol breaks, resulting in a peak of M over Z. If you look at the 1-methyl 1-methyl cyclopentanol, that is the one that had a CH3 in that place. So if I break it, it gives two parts. It gives the part with the OH and the part of the methyl group. So the part with the OH is now C5H9O. That is an M over Z of 85. And the other species, due to the breakup of that, is the CH3 plus. Remember that any species that you talk about when we're talking about mass spectrum must have a positive sign because all of these are positive ions in the mass spectrum. Question 3 says, a saturated solution of barium hydroxide was formed by adding barium oxide to water until no more would dissolve. The equation for the reaction is this. So he's first dissolving barium oxide in water to form barium hydroxide. Then the resulting mixture was filtered to remove the excess solid. The concentration of the barium hydroxide solution was found by titrating portions of this solution with hydrochloric acid of known concentration. So he's going to take the barium hydroxide solution, titrate it with HCl in order to determine its concentration. He used 10 centimeter cube portions of the barium hydroxide solution in conical flasks. He titrated it with HCl that had a concentration of 0.2. 3 drops of methyl orange was added to the solution in each conical flask. Remember, the conical flask has barium hydroxide. So what is the color of the methyl orange if you have barium hydroxide? It is yellow, and then at the end point, when it is neutral, the methyl orange becomes orange. Then he says, complete this table. So this is the table of his results. In experiment 4, you're supposed to get the final burette reading. If the difference was 21.9, then the final is the total of both. In experiment 3, you're supposed to get the titer. That means the difference between them. Then he says, give a reason why the first titer should not be used to calculate the mean titer. Remember, when we repeat the titration several times, we look at the ones that are concordant. Concordant means they are within 0.2 of each other. Now, experiment 1 is not concordant. That means it's far away from the others. It is not within 0.2 centimeter cubed of the other, so we cannot use it. Then he says, calculate the number of moles of hydrochloric acid in the mean titer. That means I need to get the average of the concordant results. So I'm getting the average of those that are within zero point 0.2 of each other. That means that the volume of the HCl would be the average of experiment 2, 3, and 4. That gives me a certain volume of HCl. The number of moles of the HCl would be the concentration times volume. In the question, he tells me that the concentration of the HCl was 0.2, and the volume, you remember, we should divide by 1,000. It needs to be in decimeter cubed. That gives me a number of moles of HCl of 0.00437. Then he says, calculate the concentration of barium hydroxide in the solution. So first of all, I got the number of moles of HCl. You should realize from the question, from the equation above, that the number of moles of the barium hydroxide should be half of that. You can see that the equation says 1 mole of barium hydroxide reacts with 2 moles of HCl. That means number of moles of barium hydroxide is half of what we got for the HCl. From that, I can get mass, but this is the mass in 10 centimeter cube. Remember that he took 10 centimeter cube of the solution and did titration. So the mass is number of moles times the MR, and that comes out to be 0.374 grams in the 10 centimeter cube. Now he's telling me he wants it per decimeter cubed, so I can get the mass in 1,000. If this is in 10, then how much in 1,000? So this is the mass in 1,000. So this is actually 37.4 gram per decimeter cube. Then he says solid samples of soluble barium compounds such as barium oxide are toxic by inhalation, so I shouldn't breathe them. Give a safety precaution that should be used to minimize this risk. Remember, we said if we're talking about something that is toxic and should not be breathed in, then we use what we call a fume cupboard. So we say do the experiment in a fume cupboard. Barium also forms a peroxide. The bottle of peroxide has this hazard symbol. What is the meaning of this symbol? You are required to know the meanings of the different hazard symbols. This one means oxidizing agent. If you look at the hazard symbols that you're supposed to know, remember that the one he gives me is not flammable, it is oxidizing agent. So there is one for flammable, and there is one for oxidizing agent, plus the other is corrosive, toxic, and so on. You should be familiar with these hazard symbols. Question 4 says, a sample of 1 bromobutane may be prepared by reacting butane 1-all with sodium bromide and 50% concentrated sulfuric acid. So he gives the procedure. Let's just go through it very quickly. Add suitable quantities of butane 1-all and sodium bromide to a round bottom flask. So he's adding the alcohol with the sodium bromide in a flask. Place the flask in a cold water bath and add concentrated sulfuric acid drop by drop to the flask. Remember, when we're working with concentrated sulfuric acid, the reaction is always very vigorous. It could be very exothermic, and that is why he's placing it in a cold water bath, and that is why he's adding it drop by drop. We cannot add concentrate sulfuric acid all at once, or the reaction would be too vigorous. Then he says heat the mixture under reflux for about 45 minutes. Rearrange the apparatus for distillation. Distill the reaction mixture. The distillate collected contains 1 bromobutane and water in separate layers. Remove as much of the water layer as possible. Transfer the impure 1 bromobutane to a separating funnel. Add sodium hydrogen carbonate solution. Remember that this was a reaction that contained sulfuric acid. We may have added a lot, or usually we add actually excess of sulfuric acid. So he needs to put sodium hydrogen carbonate in order to neutralize any excess acid in the solution. Shake the mixture, run off the organic layer into a clean conical flask. Now in step 5, he adds anhydrous calcium chloride. You should remember in your mind that anhydrous calcium chloride is a dehydrating agent that soaks up any water from the solution or from whatever we're trying to dry out. Stopper the flask, allow it to stand, decant the liquid, Distill the product over a suitable temperature range to give pure 1-bromobutane. So he gives me a data table with density, molar mass, boiling temperature of each one. Suggests why the percentage yield of 1-bromobutane might be lower if the cold water bath was not used. Remember we said, why do we use the cold water bath? We use it because the reaction is very vigorous or very exothermic. So if I don't use it, the solution may boil over, and that means some of the solution will be lost by splashing, and that means the percent yield will be lower than it should be. Now state what must be added to the mixture in the flask before heating. Remember, this was when he was heating it for reflux. You need to add anti-bumping granules before you heat in under reflux. This is the kind of apparatus. So when he says draw a label diagram of the apparatus you would use for heating under reflux, this is the kind of apparatus that we use. You need anti-bumping granules so that the solution that is being heated does not boil vigorously and jump out into the condenser. We have the condenser vertically on the flask. This is what we call heating under reflux. Remember, the water goes in from the bottom, comes out from the top of the condenser. Okay. Then he says, state why sodium hydrogen carbonate solution is added in step 4. Remember we said sodium hydrogen carbonate is something that reacts with acid, so we add it to neutralize the excess acid, any excess sulfuric acid that is in the solution. Then addition of sodium hydrogen carbonate in step 4 causes vigorous effervescence. Explain how the problem associated with step 4 should be dealt with. Remember, he was doing all of this in a separating funnel. If I have in my separating funnel something that gives out a lot of gas, I should, first of all, when it is upright, I should remove the stopper. So this releases any gas that is built up or any pressure that is built up inside the separating funnel. And then I close the stopper, invert the funnel, and open the tap so that it gives out a gas from the other side of the solution. This helps to remove any excess gases that build up inside the solution that would cause increase in pressure. Give the purpose of anhydrous calcium chloride. Always remember, anhydrous calcium chloride is a drying agent that is added to remove water. State how the appearance of the organic liquid would change. When I add anhydrous calcium chloride, the solution with a bit of water is usually cloudy. Now, when I add the drying agent and it removes water from the solution, the cloudy solution becomes clear. For the final distillation in step 6, a thermometer with a scale giving readings to the nearest 1 degree Celsius was provided. Give a suitable temperature range for the collection of the pure 1-bromobutane. Now, if we look at the table that he gave us, he said the boiling temperature of 1-bromobutane is 102 and the butanol is 118. Now, I want to collect only 1-bromobutane. So I want to collect within a range that is around the boiling temperature of 1-bromobutane, and that is nowhere near the boiling temperature of butanol. So the maximum I can collect to is about 105. So you can say about 100 to 105 or something around that range, but not much higher, or you will start to collect butanol with it. A student was asked to prepare 20 centimeter cubed of 1-bromobutane using the procedure described. The student knew that the percentage yield would be less than 100. First of all, give one possible reason why the yield would be less than 100. Remember that there could be incomplete reaction. Not all the butanol was changed to bromobutane. Then he says, after some research, the student decided to use 21 grams of butanol to prepare 20 centimeter cubed of 1-bromobutane. Calculate the percentage yield that the student expected to obtain. we go back to the information that he gives us. He gives us in the table the density of each one, the molar mass of each one. So I can use this to calculate how much he should get of the bromobutane. So first of all, he says he has 21 grams of butanol. Well, the number of moles would be the mass over the molar mass. He already gives me the molar mass of the butanol up there, so I get the number of moles of butanol. And then from the equation that he gave me, the number of moles of butanol is the same as the number of moles of bromobutane. That means that I can get the mass of bromobutane that he should get from the 21 grams of butanol. That comes out to be about 38.88 grams of bromobutane that he should get. But then he has a volume. The solution is, or the compound is in a volume of 20 centimeter cubed. So I need to determine what is the volume of the 38.88. I use the density. Density is mass over volume, so the volume is mass over density, and that means that if he starts with 21 grams of butanol, he should get 30.6 centimeter cubed of the bromobutane, but he's saying he got 20. So the percent yield is what he got over what he actually should have gotten times 100, and that is 65.3%. And that's the end for this paper. I hope this was useful. Thank you for listening.